Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar on CIA NEXGen durability in a marine environment. The CIA NEXGen series of webinars are organised and presented by the young professional members of the CIA to promote topics and generate interest from their point of view. They present a fresh approach to excellence in concrete. In this webinar, Amanda Ryan and Lewis Buckland will present on the durability of concrete in a marine environment. I'm now going to invite Josh Tappis to introduce our speakers and topics, and a few words about Josh. In the last 3 years, Josh worked as a research associate at the UTS Boral Centre for Sustainable Building, where she carried out significant work on the development of low-carbon cement and concrete, with particular focus on durability and phase development. She also co-supervises multiple PhD projects and lectures for the subject, Design for Durability. Josh holds a bachelor and master's degree in materials engineering and a PhD in civil engineering materials from the University of Technology, Sydney. She's an active member of the Concrete Institute of Australia, in the Young Professionals Group, and the CIA New South Wales Committee. And she's also the current Rollum Youth Council representative for the Pacific region. Ladies and gentlemen, please join with me in extending a very warm welcome to Josh Tappis.
Thank you very much, John. It is my pleasure to introduce our first speaker for this afternoon, Amanda Ryan, to talk about the durability of wharf construction and repair. Amanda is a project engineer for Duratec Limited. After completing her degree in civil engineering in Edinburgh, she went on to fill various roles as an engineer working on projects and assets in New Zealand and Australia. In the past few years, Amanda has been working on numerous marine projects for defense, including the most recent construction of the Armament Wharf extension and the current design and construct project, Oxley Wharf extension. Please welcome our first speaker for this afternoon, Amanda Ryan.
Thanks, Joshua. Hi everyone. Today I'm going to speak to you about a couple of projects that I've recently worked on Garden Island. It's a naval base off Rockingham off the coast of WA. So first project was MA2, MA3 remediation project. Duratec Australia were engaged by Defence to carry out works on Armament Wharf, Garden Island. We were engaged to take visual investigation of 6 piles. They were raker piles and also straight piles. They were steel structure piles coated with concrete coating, approximately 560 millimeter in diameter. And the first picture here, you will see a pile defect during our survey. So visual and delamination survey was undertaken on every pile. As you can see on the photo on the right here is where the delamination occurred. Large areas on the concrete surface of the pile were delaminated, and here we found exhibit defects of alkali-silica reaction. You may ask, what is alkali-silica reaction? Well, it's most commonly known as, you've probably heard of, concrete cancer. It's when the swelling reaction that occurs over time in the reinforcement, when it swells and then it forms a concrete outside it to crack, therefore letting air and moisture into it, deteriorating the reinforcement structure further. So the hull condition, in general, the cracks were noted were a lot wider than 0.3 millimeter, which is quite wide for a crack. They like to say anything above 0.2 should be remediated or repaired. So our cracks are quite large. They were found towards the soffit. Average length was about 2 meters. Spalling locations were relatively all around the cracks, and localized rust stain, as you can see from the photos, were around the cracks as well. And in some areas, there's even exposed reinforcement. So the pile condition, this photo here, it shows etching exposed the aggregates as deep as 20 millimeter were exposed. And here on various piles, it showed carbonation and chloride ingress. And carbonation of concrete is a chemical reaction between carbon dioxide in the air and calcium hydroxide. It's mainly when the passive layer breaks down due to the carbonation, the bond between the steel and the concrete is broken. So we did a further inspection on the piles. So removing the concrete, we did a concrete breakout, exposing the steel, and then we undertook a non-destructive test called a UT test, ultrasonic test. It was taken on 8 spots. Measurements were taken along the pile circumference and equally spaced locations. And with the results from this, we proposed it to the client, and they proposed a repair for each pile. So there were 2 repair methods that were proposed depending on the delamination of each pile. So for the first repair method, so it involved a minor breakout. So minor breakout of the delamination area. So we broke back the concrete to the exposed steel. We then coated the steel with a zinc-rich coating. This is what this grey paint looks like here. Then we formed it with formwork, and we poured a repair mortar known as Phosroc HB20. And this photo down here just shows the post-repair mortar when it's curing. So cured for its X amount of time, and then we installed a pile jacket. I'll go through the installation of the pile jacket in the next slide. So for larger breakout areas, we once again broke back the concrete to the bare steel, and this time where the steel was that deteriorated that we couldn't just apply the zinc-rich primer. We had to do further repair methods. So we had to steel strengthen the pile. So then we installed a 12 millimeter steel plate to the pile, which is this. So it's the radius of the pile, and fully welded, 8 millimeter fully weld on every side. And then over that, we installed the pile jacket. So the pile jacket installation consists of, it's like marine piling paint, I think, or petroleum-based primer, it's known as. So it's almost like a really sticky paint. You paint it on to the whole surface of the pile, and then you wrap it in pile protective tape, which is this section here, and then you apply the jacket. So the jacket is installed with using a hydraulic jack. So that was completed to all the piles that had those steel plates. And this shows the jacket itself in full. So this is one of the raker piles that were remediated, and this just shows the top, and here are the bolts that go through. You basically wrap it around the circumference of the pile, put the bolts through, and use a hydraulic jack to tighten it. And when you tighten it, the jacket actually, because it tightens, it actually pulls down a bit, so you're left with almost 10-20 mil gap from the soffit. So we install what's known as, like, it's almost like a sealant on the top, just to so no water ingress is able to get into that area. So that was that project. The next one I worked on was a wharf project, so wharf construction. It was a joint venture with Airtech, and the scope of works was to supply, fabricate, and place reinforcement, supply, mix, test, place, and cure concrete to specification in a marine environment. Started this project in 2020, and due to the duration of the project, we'd be pouring some concrete pours in the summer months. There were a number of restrictions within the specification that we had to take into account and acknowledge. And the first one was talk about temperature and limits on evaporation. So some of the specifications and limits were the concrete cannot be poured if temperature was less than 10 degrees or exceeded 32 degrees Celsius. If the ambient air temperature was greater than 38 degrees, if there was heavy rain, or if wind conditions exceeded 10 kilometers an hour, we had to put a windbreaking system in place, which was the majority of the summer. There always had to be a windbreaking system in place because especially we were highly exposed out in the ocean. We had some high winds come through there, often getting up to even 50k. So the mixed design, we did a mixed design trial, and the requirement for durability dictated the requirements to try different binder regimes. We included silica fume in the mix to assist with the slump and workability, and overall in general, using silica fume, more chemicals are required. We received a lower slump, and the risk of crusting due to harsh environment was more pronounced in the silica fume mix. We also exhibited jelly set, which you can see here, which is cracks forming when the concrete is still in its plastic state. And the mix with silica fume was a lot more challenging to obtain any desired finish, and it included, or it required extra troweling and a lot more curing time and effort. This was the mix without silica fume. So this low heat mix definitely had a desired slump. We exhibited no jelly setting, no visible cracking, and yet the bleed characteristics allowed DGV to obtain a desired finish. It was easier trowel and easier broom, which is this photo here, is a broom finish, which is the requirement for our slab. So heat of hydration, how to monitor the heat in the concrete, especially in the larger pores. So within the spec requirement, we were to monitor larger pores, and larger pores were considered where one face of the slab was larger than 1 meter. And to do this, I installed temperature sensors. So temperature sensors were from a company called SmartRock, or Guytech SmartRock sensors. So basically download an app on your phone, the SmartRock app, install the sensors in the reel at 3 different locations, installed one, say 300 mil from the bottom, one in the middle, and 300 mil down from the top. So we're getting the bottom, middle, and top temperatures throughout the concrete. And it's monitored at every 30 minutes for 120 hours. And with our pores, the core of the slab, the specification requirement for the core of the slab was not to exceed 75 degrees Celsius, and the core and external surface not to exceed 25 degrees Celsius. So we did a couple of trials to ensure that we were going to get it. So 3 trials in total we did, and we conducted for large pores to determine the critical conditions met by appropriate measures of controlled heat in the concrete. So here we have insulated forms. We did a 1.5 by 1.5 cube with insulated forms, single ply in the bottom, and sides were insulated with expanded polystyrene sheets. Temperature probes were installed, top and cured with aliphatic alcohol, which is this blue liquid, and then trowel finished, which you can just see here. And this is a curing, so we left to cure for 14 days with water running for 14 days. So our water cured. And here are the results. So this is what, once you download all your results from your app for the heat, for the temperature probes, this is you download it on and you get a spreadsheet, and then this is what it shows. So for the bottom probe is this middle one here. The top probe is this blue line. And we have the middle probe, which is our highest, which expected highest temperature is this one. And this is your ambient temperature. So the trial was successful with a max temperature of 68 degrees Celsius. And the max temperature internal differential was 13.9 degrees Celsius. And our ambient temperature at that time was 19.3 degrees Celsius, and our slump was 160. The trial, it had Hessian and sprinklers on, reflection, insulation, and tarpaulin on top curing for the curing period. And this was undertaken on 24th of June. And all this was downloaded after 120 hours. So next we decided to trial with ice. In case we got really high temperatures, we wanted to ensure we had a backup plan. And we thought we'd trial the mix with ice. So due to the timing, the concrete was placed in cooling months where temperature had to be conducted during this period. I think a week of 35 degrees Celsius and days concerning. So all materials, you have to consider all the materials, such as the materials that go into the mix are left out in the heat. They're not always covered. They're not always sprinkled, like they don't always have water sprinkler on them for 24/7. So sometimes the materials in the summer months are a lot hotter, a lot warmer. So you have to take that into account as well as the ambient temperature. So the trial with ice was, unfortunately not satisfactory due to the effect of the chemical reaction of the additives. So our mix design, it was a specific mix. It's not your standard average. It is a very specified mix. It has a lot of additives in it. And it also had a material which was known as Cypex in it. And that reaction as well with additives and ice, it just wasn't happy. It didn't work. So unfortunately, we got a delayed reaction on the slump. As you can see here, it's a pretty low slump, as our slump specification was 160 plus or minus 40. This slump, I think I remember, is 80 mil, which is way out of spec. So yeah, the addition to water with the allowable limits had no effect. So when the concrete comes to site, you have X amount of water left over that you can use to adjust the slump, which way if you need to. And I think usually with our mix, we would have approximately 60 litres of water left over. And even with adding 6 litres of water into a 6 meter cube truck, it didn't make much difference. It didn't even, we didn't even get the specification, the slump spec. So yeah, it was a bit of a failure. And the temperature, so the temperature of the concrete only went down 2 degrees Celsius, which is not a drastic amount. So we rejected 2 loads, and all loads reacted different behavior. And so the behavior cannot be predicted. So we choose not to go with that. It was just too unpredictable and too risky for what it was worth. So after undertaking all the trials going forward, we knew our mix, we can meet temperature requirements in larger pours. Using ice was definitely not an option. So you need to be cautious, especially on weather days when we pour concrete. And that's everything. This is just the last photo of showing the most recent wharf that we constructed, Arnott Wharf extension. Thank you.
Thank you very much, Amanda. That was an excellent presentation. There's actually already one question in the Q&A box, but we'll answer all those after the presentation of Louis. Okay, so again, thank you. And now it's time to introduce our second speaker for this afternoon. He will talk about the design tips for durability of concrete marine structures. His name is Louis Buckland. Louis is a marine structural engineer for Woolbridge Gilbert Aztec, or WGA, with over 4 years of experience within the marine sector. His experience ranges across marine infrastructure design, remediation of concrete structures, and asset management and sustaining capital. Please welcome our second young speaker for this afternoon, Louis Buckland.
Yeah, thanks, Josh. Afternoon, everyone. So just thought I'd, thanks for the CAA for putting on the event as well. Just thought I'd take the time to give a real high-level overview of some of the things that I've picked up for marine durability over my years, sort of doing a few quirky projects over the time. So this is my first time speaking, which I'm sure will become apparent over the next 20 minutes, but if I can just get to the next slide. There we go. There's sort of 3 key areas of focus that I really wanted to touch on. Just and again, just from those personal experiences, there's probably been some really technical presentations and some really in-depth knowledge that I've definitely been to over the years in the CA events. Yeah, this won't be one of them. This is more of that high-level overview of just some of the things that can go wrong, some of the lessons that I've learned along the way, and then just some of the durability tips that I've also sort of picked up and we've managed to pick up within our office. And I'll just start by just giving sort of an overview, and especially for the younger engineers out there, like durability, it's not always based on that technical understanding or getting the perfect mix property and all of that. And I think it's really having that greater view of how it all comes together and how things are going to be managed through the life cycle of the project. And one thing we need to remember with this is that a lot of the marine structures in Australia, especially in WA where I'm from, is that they were built sort of in a time that we didn't have as much understanding on durability as we have now. So the deterioration of these structures has been quite accelerated, especially in current times. So although there's a lot we can do on the design level, there's also a lot that needs to be done on that sort of brownfield level and trying to pick up these structures where they're at and working with them to extend their life. Some of the other things I wanted to touch on is that although, yeah, the technical skills, they're great and all of that, the communication as well, it's a really big part of it, especially considering that the client's going to pay for these things. We've got to design these things and the contractor's got to build them, and all of those things working together is what really leads to good practices for durability. So starting off with the lessons learned, just pulled this one job here. It was just in a harbour in Perth Metropolitan. It's quite an interesting example. I thought I'd look at it as a bit of an oversight because, as you can tell, I'll just bring up this laser pointer. Where is it? You can see on the right-hand side here, they've sort of designed it in a way that we've got some precast concrete planks that have been installed to span over the piles, and just to the right of this photo here, it goes over the water. So that was sort of quite standard practice. And then on the left-hand side, they've poured an in-situ slab. And you can start to see that the sand's really starting to erode underneath that in-situ component of the slab. And I guess what's really interesting about this one is that they've put in a rock revetment, and it's quite heavy duty for where it is. And then they've designed the concrete really well. I mean, for something that's sort of 30 plus years old, the concrete's in really good condition. And from a design point of view, everything was done correctly. But what's happened is that when they've put in this rock revetment, they've only really, at least from our understanding, from our investigation, just considered the wave actions. And for that matter, the revetment's doing its job. But there was a bit of an oversight for the king tides, or the really high tides and storm surge that come through. And what's happened is they've sort of just left that. And as they come up, they've sort of started to slowly wash away some of the sand that this slab, the in-situ slab, was poured on originally, which has then caused that fines to wash away, which has caused the erosion. And then it's really started to eat away at this slab. And just noting that this in-situ slab was never designed to span like its friend on the right-hand side there. So I think it's an interesting one because failure was not due to the actual concrete itself. Everything was done correctly, yet the oversight for the lack of the tides there sort of just shows that durability can be in that bigger picture side of things. So that's one there. Another one, and this was just around the corner from that side as well, is the poor planning. And again, it wasn't like too much was done wrong. It was just these simple oversights within the durability space, which has caused these major not major, but large concerns for the client down the track. And as you see here, you've got an old seawall, I guess, a bit of an in situ combination. We're not 100% sure what it was doing back in the day, but as we've expanded, they've decided to build out, and they've built out a structure above, as you see, but they've decided to span that over the water. Just on the right-hand side of this photo, we've got our water in the harbour, and they've done that with steel piles and steel, and obviously steel is not in great condition, but this is about concrete. But what they've done in that poor planning is they haven't really considered the fact that because the concrete was already there, it was already deteriorating and was going to continue to deteriorate probably at an accelerated rate. And so they've decided to, or whoever made the decision at the time, that they've used that as a structural support for the rest of the building, which keeps going out. And although the steel members can probably be somewhat easily replaced, what we can't do is replace that concrete because there was just no access. I mean, to get in there just as one person was hard enough, but let alone getting in the plant that you need or getting in a team of workers or whatever is required it was just not an option. So they've kept building out, and they haven't really thought that this existing seawall was part of the primary load path of the structure. And as it's deteriorating, it's almost at a point now where that seawall is effectively just not got the capacity to provide what it needs to. So again, this is sort of a small oversight once 20, 30 years down the track. And you've basically got a situation where the client has really, they're in a bit of strife with this one because they probably have to rebuild the whole thing. I mean, that's an ongoing process, but they really have to do a lot of work right now with something that could have been isolated early in the piece and thought about whether that was to remediate or whether that was to protect or coat the concrete or just have a mind for durability in the long term. Now that it's too far down, too far gone. So we'll go to the next one. And this is like it's a segue into that inspection piece that comes with a lot of these existing concrete structures that we sort of see in the marine environment. With a lot of the time, we don't really have these stringent inspection or maintenance strategies put in place for the structures that we see. And when we do come, it's usually when something seriously has been noticed. And a lot of the time when that's the case, as you can see down on the right here, this is just at a jetty, again, just in a harbour, a bit more of an industrial piece, so it's got some heavy loads above. But when we were called into the scene, the cracking on the soffit was pretty severe, and to the point probably where we've got probably a reduced capacity from the jetty above. So if that was picked up early because they had a regular inspection and maintenance strategy, then these things can be quite easily dealt with, and you don't have the headache it's now caused for the operator of this jetty where he doesn't know if he can actually use it to its full capability, and there's going to be a lot more costs and a lot more time and stress involved with making sure that this is sufficient. And obviously in these environments, there is remediation and corrective action. I'm sure you could speak to Amanda afterwards and she'll go through how it can be done. But for the client, or at least the operators, it's a large outgoing for something that probably could have been quite easily fixed. And it's just, it goes back to that, the lessee, they can sometimes lack the knowledge that I guess we have in engineering or within this field, and just lack the understanding of the long-term effects of these of deterioration. And this is a real-world example to bring it up where, just if everyone remembers back to October 2018, a place called Rottnest. I'm sure everyone's heard of it for a holiday, get a selfie with a quokka. So they actually had a major failure back in 2018. And for me, this was a real wake-up call. It was very early on in my career when this happened, and it resonated with me that it's not like these things can't happen. This did, and it was really lucky that there wasn't serious consequences, but it was pretty bad. And again, it's just more that sort of reason for durability being something to consider and take really seriously. So, which leads on to the lessons learned piece that I'll try and cover here. I guess the first, I just wanted to touch on really the slides that I talked about before. What the lessons learned was for the remediation pieces that we had to do was, well, they were quite difficult. You know, they were really hard to get to places. We were also in positions where the client itself didn't want to throw ridiculous amounts of money at it. there was a piece around what their long-term plans were for the buildings in the area, and we sort of had to toe that fine line about, well, we need to do something now because it's going to get worse, but equally we don't want to go and throw the kitchen sink at it because it's probably going to cost more than potentially just doing it again from scratch. So as you can see here, we where that sand was really eroding because of the tides, all we could think of was, I mean, and I'm sure there's some more solutions and we're implementing some more longer term stuff now, but as that temporary measure, we put down A34 geotextile across the entire length of the abutment. And then we've just weighed that down with hundreds and hundreds of Hessian bags filled with a sort of cement sand mixture. It's quite agricultural, but equally for that temporary case, we had to do something then and there. And it was a lot of work. I mean, you can imagine the workers at the time, I probably wasn't their favorite engineer, but they did it. But this is holding up now, but equally there's still that uncertainty and there's still ongoing conversations on what the long-term plan is now, just because of that one sort of oversight originally. And it was a very cost-intensive temporary solution as well. So again, going back to the next slide, from the lessons learned, same problems really. Again, there was very little we could do with the access constraints to be able to remediate that concrete seawall, and because it was load bearing, all we could do was just put in that temporary case to take the load off the seawall for the best that we could at the time, and just buy the client some time to figure out their long-term strategies. So, I mean, here, yeah, really what we're looking at is small things that have just grown into some really large problems, and basically caused businesses to have to recalibrate what their long-term plans are for an area just because of some small durability constraints. So that leads on to some of the lessons learned along the way. I've got a few, so the first one that I wanted to really talk to, and probably tailored towards the younger engineers, some more experience has out there, probably know all this stuff, but is just the piece of the early contractor and early client involvement. I mean, when you're a designer, or whether you're a contractor or whether you're the client, the earlier these conversations happen between all parties, they're really powerful, and they're just a fundamental requirement. So if the designer can sort of collaborate with the contractor to figure out what their constraints are, what their capabilities are, what they know, what their past experiences are, and how they've found things to work on previous projects, and then from a design side, you can implement that as well. I mean, that's a really powerful tool to be able to have that, and then to let the client know that, and what's gone wrong in the life cycle and what's gone right as well, and then the client can budget for that and they can plan for that. I would say that's one of the most powerful things within getting durability right in the marine environment. The other part is that communicating the risks associated. So not that I'd show this slide to every client I met, never get a job again, but really it's just showing that if you don't do the right side of durability now within your concrete mix or your concrete design, or designing around the concrete itself, so it's got that ability to withstand the environment, then the costs down the track are going to be quite significant. So just start letting the client know that, and really communicating that early in the piece. And we've got some really good parts, or some really good tools, such as your safety and design, your quality plans that exist, inspection and maintenance plans. So we can use those tools and use them to really implement some positive durability. And most importantly, I think, it's fun. It's one of the funnest things about engineering, is being able to work in that team, especially in that conceptual phase. Is everyone gets to share their knowledge and contribute. So, I sort of bring up just an example here about one of the things where one of my shortcomings was, thankfully, just early on. But I always just assumed concrete was just poured and that was that, and it all sort of lent on the mixed design, or how, from the design side of things, how it's mixed, but never really appreciated the fact that it needs to be pumped there, and there's constraints and limitations within pumping concrete, especially in a marine environment. You can't just drive a concrete truck out to a recently constructed wharf or whatever it might be. And I actually went to a CIO presentation where one of the guys who was a specialist in pumping concrete spoke quite in depth about some of the problems that he's come along the way, and how to overcome them. And that in its own right sort of made me realize that there's just so much more to getting this right than just getting that design correct originally. So I suppose that's one side of it, and that leads on to that. Never underestimate the power of the worker. You know, they know things, and they've usually done a fair bit of it. So the more that you can chat to people and their past experiences, the more that you can learn and better implement for the future. And that's that. You build your network that way, and by getting to know the right people, you can really handle durability on quite a proactive sense. So that's sort of a high-level summary of some of the lessons that I've learned. And now I suppose what I'll do is just jump into a few little durability tips along the way that I've sort of picked up, and keeping in mind that these are just sort of from my experience. I don't use these like gospel. Always think through the problem uniquely and how it's going to best work for anyone's specific project, whatever side you sit on in that. But the first one of these is just the power of technology these days. So, I mean, you know, we're not where we were 20, 30 years ago, where everything was done sort of manually and scrutinously. You know, we've got these things like an ROV here, which is fantastic for investigating and inspecting underwater concrete structures, and it saves a lot of labour and a lot of man hours with the dive team. So you know, being able to utilise these in the right environment and understanding when's the right place to use them, what their capabilities are, and when's the right time to go, you know, that's not what I'm going to use. I'm actually going to use a dive team here because I know I'm going to get a better purchase, and that's equal for using your drones or your UAVs. So, I mean, these things can just get to, especially sort of soffits on wharfs and jetties, concrete stuff like that. If you don't have the inspection vessel, then what you can do with the drone in a very short amount of time is quite impressive. So, and then the photogrammetry piece, that's sort of a strong work in progress. Yeah, it's really cool. And I think being up to date with all that stuff and understanding it and where it can be applicable for you is good, because the more you understand about the defect or the concrete or how it's acting in its environment, or what might be the factors that are causing for the ongoing deterioration, or what might be doing really well and causing it to sort of withstand the environmental the loads, the longer it goes into getting the solution right and how you can benefit or long-term durability of whether it's that structure or one that you're going to be involved in the future. The next one of these is, know your people, know the market. So just learning what products are out there and using the right product where applicable to maximise your structure's durability. So just to name a few of them, I mean, there's so many, and they're all quite incredible in their own right. But you've got your glass fibre reinforced polymer reinforcement, stainless steel reinforcement, knowing when's a really good time to use that, knowing when maybe you might have to revert back to your traditional galvanized or mild steel reel, or whatever it might be, and just the limitations and the strengths. Your concrete admixtures as well. I mean, they're incredible in what they can do. So, and each of them probably brings something unique to the table in many respects. Same with the coatings, the resins, the epoxies, so and the cathodic protection too. So, I mean, and one thing as well is it's not up to the engineer or whoever or the builder to know every single thing about one of these products, but you just sort of need to know who to ask. So it's really good to network and find out, meet suppliers, meet specialists, and get them on board for what you're doing as well, and communicating what your problems are and letting them really share their knowledge. And in my experience, they've just always been willing to help. And if they're not, they're probably in the wrong industry. So the next one here, probably a bit of a little design tip that I've sort of come across a few times now. This is just one example, but again, it's sort of thinking about what can go wrong. And in this case, it did go wrong, and then how that could be done better in the future, and something that you can carry forward. So this here was just a concrete element, sort of a dolphin that was exposed to some pretty open seas. Within those open seas, there's potential to have floating debris, whatever that might be, and there can be some pretty heavy, especially in where this was located, some pretty heavy wind loads, some pretty heavy wave loads. So what we think happened here is something's hit this concrete on the corner, and it's just sheared off the corner of the concrete. It's got no implications on the actual strength of the dolphin itself, but what it has done is it's completely knocked the cover off, which has then allowed for that real accelerated corrosion and chloride penetration throughout the whole element itself. So that loss of cover is not good. And again, it's out of sight. So no one really notices that from above the deck, and it's at a position where you're just not really seeing it. So we only picked that up from doing a drone survey. We've noticed that corrosion's not looking great. It's probably still got time to remove, but it needs to be remediated. But in order to mitigate that in the future, something that sort of talked about was, well, there's fibre reinforcement that's out there, especially the little glass fibre reinforcement that you can chuck in, which will into your concrete mix, and that'll increase the tensile strength over the entire element, especially in those corners. Obviously, you still use your traditional bars to get your strength and whatnot, but just having those fibres involved in there as well probably would have given that corner the strength to withstand some of those floating debris, and ultimately it reduces the need to go and set up all the temporary works and get the workers and do the remediation works required to fix up that corner there. So that was sort of one of them there, which I thought was just quite interesting, because it's a simple thing at the start, but it flows on with the theme that I guess I'm trying to get across here. But again, if you carry it forward in that way of thinking, then you can really mitigate a lot of these problems, and if they're communicated well, then everything does better. And I think as a whole industry, we sort of get on top of this. The next one here is going back to that photo that I sort of picked up earlier, I showed earlier. This one here, so probably just talking through just the difference in a marine space between the top deck of the concrete and the soffit, and just how much more important it is for the soffit to not crack compared to the top deck, just through the exposure and proximity to the water. So one of the things that we've sort of found, and I've lent on some pretty experienced heads, is that if you're in environments where your AS 4997 in them will say that you should always use sort of 50 MPa concrete, and across the board, I think it's a pretty good benchmark. But if there's environments where that might not be possible, or that's going to be hard to achieve, or you're struggling, it's understanding the root cause of why you needed to use that higher mix, and that's really just to reduce cracking, and especially on the soffit side. So if that's the case, then you can look at ways to increase your bar size, or design for that bottom layer of reinforcement for serviceability, and just reduce the potential for cracking instead of using the higher strength concrete, higher strength cement mix. And these things, again, you're looking at the root cause of what could go wrong, and then how to work around it. So in this environment here, we don't know what the actual cause was, but potentially if they did increase the bar size or increase that there, then maybe we wouldn't have got the cracking on the soffit, and this might have withstood a few more years. And the next one here, just got a steel pile encased in concrete. So pretty typical detail that's used throughout. What you'll find is the reason they do that is you can get your anchor bolts coming out of the top of the concrete, and that'll fix down on the headstock. And again, pretty good detail, commonly used. One thing that we have noticed, or I've noticed that's happened though, is that because you've got that nice smooth flat surface of concrete on the top, that's where your water can typically pond, and then that ponding water is what can really lead to some more accelerated corrosion, or it can lead to accelerated chloride ingress. And so again, simple things. Okay, well, what's the root cause of the problem? Oh, well, the water's ponding. So what we've done is we've looked at starting to get some epoxies, and whenever we've got these flat concrete surfaces in the marine environment, it's just building up an epoxy layer that slopes away from the center, so that any water that does get there has got that pathway to basically drain off. So that and that in itself, I think, it's not going to be bulletproof for the rest of the time, but it'll go a long way in increasing that structure's lifespan and stopping any form of accelerated corrosion. But yeah, so I suppose that's really it from me. If I've raced through that, I apologize, but any questions?
Thank you very much, Luis. Certainly, I've picked up quite a lot of tips from your presentation. I will probably go with a Q&A session now, starting with Amanda, to give time for people to type in the questions for Luis. So for Amanda, there's a question from Tianxing of UTS about the ASR damaged part. Was there any evaluation of the residual strength for the ASR damaged structure?
On this structure, no, there wasn't. Unfortunately, the structure itself was quite old and hadn't been maintained, hadn't been inspected for, I don't even know if they had any inspection records on this structure. So when we were engaged, it was in quite a lot of need for repair. But looking at structures like this, you would regularly have inspections every couple of years, if not depending on the design life and the structure itself and how often it's used. But we would usually do inspections quite often. So this circumstance, there hadn't been any inspection done on the wharf. That's why the deterioration was quite substantial. And I like nowadays, I think Lewis touched on it with regards inspection methods and types of equipment that you use now. There's so many out there that there is no reason for a structure to get to that extreme. You would not even need to do a destructive test to figure out that there is something wrong with the structure, and it could be maintained a lot quicker, and reducing it, getting to that extreme. Yeah, I hope that kind of answers that for you.
Yeah, just a quick follow-up on that, Amanda. I actually did my PhD on ASR mitigation. It's quite a personal interest of mine. So
Okay.
just a question. So when you concluded it was an ASR defect, I was assuming it was sent for a proper petrographic analysis to conclude the ASR products, correct?
Yep.
And so I'm assuming because it's ASR, there was no SEM used for the structure.
No.
No slag in the binder. Okay. Yeah. That was just interesting for me. Okay. Now we'll go to Melanie. There's a question from Melanie. Questions about the high temperature pour. What was the maximum concrete placement temperature achieved without ice? What were the dimensions of the concrete elements? What were the mean ambient temperatures? What was the cement blend without silica fume? And finally, which additives reacted with the ice? Those were quite a lot of questions. I think it's relevant to the DF mitigation.
Okay, so the first one, what was the max concrete placement temperature achieved without ice? So max concrete temperature placed was 28 degrees, and our spec max allowable was 32 degrees. So we were close to the max. What are the dimensions of the concrete elements? So we were pouring, our slabs were approximately 25 meters wide by 12 meters long, and it was 800 mil in depth. Would have been about almost 280 to 300 meters cubed in concrete a pour. What were the mean ambient temperatures? That one is kind of hard to give, because we poured throughout summer and winter, because we had quite many pours to do. So I'm not sure the overall mean ambient temperature was, but we didn't exceed the temperatures out of the spec. So what was the cement blend without silica fume, and finally which additives reacted with ice? Okay, you're going to hate me, but I can't really speak about our mix design due to it being a defense project. Is very sensitive, and information like that is, we can't give out or speak about the exact mix design and how it is binded and what is in there, especially our additives. With regards the ice, we don't know what additives reacted with the ice, because we didn't do like a process of elimination. We just did that one trial, and when it didn't work, we could have done further trials eliminating additives to see which one works and which one doesn't, but we didn't. We just did the one trial, and when it didn't work, we didn't bother going any further with that. The strength of the concrete was 60 MPa at 28 days, and we actually received 60 MPa at about 6 days on most of our tests, which is pretty good. So it was high strength concrete, and the structure itself was constructed to a 100-year life design.
Thank you very much, Amanda. I might just go to Lewis for now. Another question from Tan Xing of a BUTS, is there any current repair method for the combined effect of ASR and chloride corrosion?
Thanks for the question there. Look, off the top of my head, not something I can probably answer super confidently. Probably not. Maybe Amanda might know, but I'm happy to get back to you. We've got some pretty good people around, but off the top of my head, so I don't know the answer to that one.
Yeah, okay, that's all right. I could imagine quite challenging, actually. I'll go to the next question from Liam. So Liam, he said, you mentioned the impact of king tides, which I assume will be more frequent events with climate change. In general, how do you predict and assess the durability impact of rare or uncommon events for existing structures?
Oh, look, absolutely. Yeah, it's something to be really mindful of. Thanks for bringing that one up, Liam. Something to be really, really mindful of. I mean, I can only speak about sort of around my little area where I live in Perth, and all the seawalls for the Swan River there, they're overflowing now, sort of 4 or 5 times a year. And when they were designed, you can imagine they were designed to not. So it's going to be something that really needs to be managed and watched, especially in that particular environment where they never thought that the tide would get there, and you only had sand as your last line of defence. So probably the two things from it is absolutely, I think sea levels are rising, and the impact of the higher tides are real. And the second part is making sure that whatever structure you're looking at is probably in a position where its last line of defence isn't going to be severely impacted by that. So,
yeah. Thank you, Lewis. Another question, I think for Lewis and Amanda. So in your years of working, doing some remediation work, so in your opinion, what's the top cause of remediation? Is it poor design, poor choice of materials, or simply just end of the service life of the structure? And do you think that in quite a lot of work you do, was there a chance to avoid the remediation? Or
yeah, I'm happy to start it off. So the first part of the question was, so what was the first part there, Josh, of the question?
Oh, the first part is like in the years of work, that you've done for marine concrete structures, remediation work. In your opinion, what's the top cause why remediation is basically required? Is it perhaps poor design, poor construction methods, poor choice of materials, or just simply like end of life of the structure? Or was there a chance that remediation work could have been basically avoided?
Yes, that's a really, really interesting point. I think everyone's got to take ownership, and I think the first thing that can't happen is the finger pointing, because that's how things tend to never get done properly or done proactively. And look, it's definitely, there's a design component, speaking from a design side, but equally, it doesn't matter how in depth or amazing your concrete design is, it's still got to be poured and done that way. So working in that team environment there to make sure that what's designed is actually going to be applicable on site is an extremely important part. And then following on with that, I think where there can be some real oversight, and this is something I've experienced, I'll probably keep it a bit high level just for the sake of it, but is within lease agreements as well. So typically there's going to be head leases, subleases, lessees. The person that's on the receiving end of the lease agreement sometimes is, maybe just running a hospitality venue, or they might be doing whatever, and at no point in time are they properly informed or have the awareness that maintenance of their structure on water is an extremely important thing. But within that lease agreement, maintaining the part that's sort of their substructure, or the part that's on water is actually part of it. So that's another part to it as well, is just making sure that whoever's actually in charge or responsible for doing the work or doing the maintenance or inspection is actually made aware of it and given the correct prompts by the people around them. So yeah, hopefully that helps.
Thank you, Lewis. I wonder if Amanda would have additional comment to that?
Yeah, on the back of what Lewis said, I pretty much agree with everything he said. There's no one person or one field that you can point at and say that that's the reason it's deteriorated or that's the reason it's failed or anything like that. It starts from design to construct. If it's not constructed to specification or constructed to the design, you have an issue there. And then also after construction, the remediation and or the inspections and remediation where required. That is a big part of it as well. And if that's not taken on and continued, well, you're gonna see some failure in it, because that's a very important section of it. And what was the second part of the question?
I think you've already answered it. Like, could have it been avoided? Yeah, for if there was
Yeah, definitely. It can always,
yeah,
it can always be avoided. Definitely.
Yes, thank you. And is there another? Just looking at all the durability issues you've mentioned, I think Amanda covered pretty much everything: ASR, carbonation, induced corrosion, chloride-induced corrosion, even DF. And for both Amanda and Lewis, if you'd rate all these deterioration mechanisms, like if you'd name the top 2 in Australia, which one would it be? Based on the work that you've done so far with marine concrete structures, the top 2 most common deterioration mechanism for marine concrete structures.
Oh, I would think chloride ingress is definitely one that I've witnessed quite a lot. That and carbonation, I think, yeah, they'd be the 2 most top I've witnessed on my projects anyway.
Right. Carbonation, despite being around wet environments.
Yeah.
Still very prominent, isn't it? Okay.
Yeah.
Yeah, with the chloride ingress from my perspective as well, just from general cracking in the concrete, whether it's shrinkage or overstressing or whatever it might be, and then just the chloride penetrating through that tends to be the most common. But yeah.
And perhaps, thank you. And I'd probably throw in my last question for both of you now. What do you think are the challenges? There's another technical question, not a question, but a comment. In Sydney, tenants that lease government-owned marine structures are required to prepare and submit a maintenance plan at the start of the lease. From Russell Howell. So something worth taking note of. So going back to the last question for Amanda and Lewis, perhaps just top of your head, the main challenges of doing remediation work for marine structures, and if you could give 1-2 tips for our young engineers that will be going into this field in the future. I know Lewis did mention quite a lot already, but
one is be very open to learning everything and anything from everyone and anyone you meet on site and off site. There's just so much to learn. There's so much to learn in this environment, in the work itself. Also be prepared if you're on site, be prepared to work long hours and weekends. Yeah, and just be open. Just always ask so many questions, because there's so much to learn, and the list goes on. It's a never-ending learning progress.
Yeah, I think Amanda's probably beating me to it there. I was probably saying something similar, but yeah, the stuff that resonates the most is the stuff that you see in person when it's gone wrong. So put yourself out there, I think, is one thing, but equally the people that have sort of seen a lot of it as well, typically people that have worked on site for a long time, their knowledge is invaluable with this sort of stuff. So it's up to us to be able to sometimes calibrate that knowledge and how to effectively manage it. But yeah, in the first place, just chatting to everyone and anyone is an extremely important tool. And then likewise, that sort of goes into the suppliers and the specialists as well, because it's pretty incredible how in-depth their knowledge can be on specific topics, and really being able to lean on their knowledge and building up a network of people in that regard for when you do come across an issue.
Thank you very much, Louis and Amanda. So I think at this point, I'd like to thank you both already for sharing with us those very, very informative presentations. I've certainly learned a lot, and I'm quite sure our young viewers did learn a lot as well. So thank you very much for being our second set of presenters for CIA NEXGen webinar series. At this point, I'll probably turn this over to John to officially close this afternoon's session.
Okay, and good. Thanks, Josh, for a job well done. And ladies and gentlemen, I ask you to join with me in thanking our three presenters, Amanda Ryan and Lewis Buckland, and our host, Josh Tappers.